Hey there, thanks for coming to check out my video. I wanted to talk to you about the Central Limit Theorem. Please don't forget to like and subscribe. The Central Limit Theorem is best demonstrated through an example. Do you remember I had you take a first day of class survey where I asked you your age and several other questions? Well, I could also go around and administer that survey to other classes. For example, I could go to accounting or EBL 400 or another class and survey the students in that class. And so by visiting different classes, as you could see here, I have several different samples that I can gather data on. And I know some of you are in accounting and some of you are in EBL. So it's possible that if I visited another class that there would be some overlap of the samples. So for each one of these samples, I want to calculate a sample mean. And so to denote the different samples from each class, I've used subscripts next to each of the means, 1 through 6 here. And so we are going to look at the sampling distribution of the sample means, which are x1 bar through x6 bar. And one really important thing that you need to know from the central limit theorem is that the mean of the sample means, or mu sub x bar, is equal to the mean of the population, or mu. But the standard deviation of the sample mean, sigma sub x bar, is also referred to as the standard error of the mean, and it is found by taking the standard deviation of the population divided by the square root of the sample size. So please get your pencil and paper and take note of this. From this point on and for the rest of the course, whenever you get n, the sample size, you have to take sigma divided by the square root of n. So I have an example here that has slips of paper with 5, 10, 15, and 20 written on them, and they're put into an urn. Why statisticians like to put things in urns is beyond me. But there's an experiment performed where two slips are randomly selected with replacement, and the selections are recorded. So with replacement means that I will pull the first slip out of the urn, record that value and put it back, and then pull another slip and record that value. So as we know, there are 4 slips of paper that have 5, 10, 15, and 20 on them. And if you were to put these into your calculator or a computing package, you would find that the average of those 4 numbers from the population is 12.5, and the standard deviation is 5.59, and therefore the variance is 31.25. These are all population parameters, okay? And here we have a histogram of the possible selections of each draw. Each draw is equally likely and has a probability of 1/4. So therefore, all of the heights of this distribution are the same, 0.25. Now, all the possible samples that I could draw go from 5.5, 5.10, 5.15, 5.20, and so on, all the way through 2020. And you can see from each of the pairs of samples here, I have the sample mean calculated. So the average of 5 and 5 is 5, whereas the average of 5 and 10 is 7.5. And we only see these couple of values, excuse me, we only see the 5 happen once. Similarly, we only see the 20 happen once. But 7.5 happens a couple of times, 12.5 happens 4 times, and so on. And so if we were to make a frequency distribution, we would have the different sample means in one column, how many times they happened out of the total 16 possible draws, and the probability of each of the sample means is given here. And so when you graph the histogram of the sample means from the two draws of the slips of paper out of the urn, you can see it is a symmetric bell-shaped distribution when you smooth it out. So the central limit theorem has two major parts. The first is that if we take a large enough sample from any distribution, whether it's bimodal or right skewed or left skewed or J or reverse J, doesn't matter the shape. If we take a large enough sample, and large enough is 30 or more in our sample size, then the sample means will be normally distributed. This is the first part of the central limit theorem. The second part says that if we sample from a normal distribution, then the sample means will also be normally distributed. So two parts of the central limit theorem, again, state that if you take a large enough sample from any distribution, the sample means will be normally distributed. And if you sample from a normal distribution, the sample means will be normally distributed. So I'm just scrolling through the notes here. Oh, look at, here we go. The mean of the sample means is equal to the mean of the population, and the standard error of the mean is happening again. You know what that means when I repeat myself? Oh, there it is again. I'm repeating myself again, so this must be really important, huh? We had an original z-score formula of x minus mu over sigma. Now we have a new and improved z-score formula, which takes into account the given sample size to calculate the sample mean. So this standardizing formula, which I will refer to as the new and improved formula, takes the sample mean x bar here instead of just x, subtracts the population mean mu, and divides all of that by what we refer to as the standard error of the mean, or sigma over the square root of n. One thing that's missing here that I was not able to add in would be parentheses around the numerator and the denominator. You have to include the parentheses around both the top and the bottom of the fraction, otherwise the order of operations will compute this value incorrectly. So earlier in this slideshow presentation, we had magnolia bushes that have an average height of 8 feet and a standard deviation of 0.7 feet. And here in this slide, 86 it looks like, 38 bushes are randomly selected from the population of all of the magnolia bushes. So here is n, our sample size, and you wrote down whenever you get n, you have to divide sigma by the square root of n. So this question asks us to find the mean and the standard error of the mean of the sampling distribution. So the mean of the population is equal to the mean of the sample mean. So the average of these 38 bushes should be about 8 feet. However, the standard deviation of the sample of 38 bushes is found by taking the standard deviation of the population 0.7 divided by the square root of n, which is 38, and we get 0.11355499948, which is a little bit more specific than this rounded value here. I do not recommend rounding in intermediate steps. I've told you this since the first night of class that you should not round. So if you were to go forward with this problem, whether it be by hand or using technology, you should really enter the entire value of the standard error of the mean, not the rounded value of 0.11 as listed here. Now we have another question on slide 88 that asks for the probability that the mean height of the 38 bushes is less than 7.8 feet. So that's asking for the probability that x bar is less than 7.8. So now that we have x bar instead of x, we have to use our new and improved z-score formula. So in order to find the probability that x bar is less than 7.8 feet, we need to standardize that value, or turn it into terms of the z distribution, which is the standard normal distribution. So we have this question, the probability that X bar, the average of all 38 bushes, is less than 7.8 feet, and we want to standardize that or transform it into a probability of Z statement. So we are going to use our new and improved Z-score formula, which is 7.8 minus 8 divided by 0.1135549948. And when we do that, we get negative 1.7612611144. This is okay to round to negative 1.76 because that's the best our table will give us is Z to 2 decimals. So if we were to consult our standard normal distribution table and find the area under the curve to the left of negative 1.76, we should get 0.0392. And there it is, 0.0392 is the probability that the average height of these 38 bushes is 7.8 feet or less. That probability is much smaller than if I were to ask you for the probability that a randomly selected magnolia bush is less than 7.8 feet. So I have a couple of examples here in the slides, and I'm going to scroll forward to this achievement test example on slide 92. So the average time it takes a group of adults to complete a certain achievement test is 46.2 minutes. That is our population mean mu, and the standard deviation of the population is 8 minutes. And we will assume that the achievement test times are normally distributed. As a matter of fact, we will assume that all of our distributions are normal unless otherwise specified. So we have a couple of questions here. Find the probability that a randomly selected adult completes the test in less than 43 minutes. And I've written that probability statement here. And part B asks for the probability that 50 randomly selected adults on average take less than 43 minutes. And I've written that probability statement here. Now, part A is going to use the original Z-score formula of x minus mu over sigma, but part B introduces a sample size of n equals 50 here, so we need to use the new and improved Z-score formula. So for the first part, the probability that x is less than 43 when we have a normally distributed variable with a mean of 46.2, and we want to know the probability that x is 43 or less, I have to standardize this value of 43 or transform this normal distribution into a standard normal distribution. So I could use my table to find the areas under the curve. So to standardize this, I take x of 43 minus the mean mu of 46.2 and divide all of that by the standard deviation of the population, sigma, which is 8. That result is negative 0.4. So in part A, the probability that a randomly selected adult completes the test in less than 43 minutes is equal to the probability is less than negative 0.4. I'm missing my negative sign right here. And so when we look up negative 0.40 on our standard normal table, we get the area under the curve to the left of that is 0.3446. So therefore, the answer to part A is 0.3446. Part B asks for the probability that 50 randomly selected adults complete the test in, on average, less than 43 minutes. So in order to standardize this question, we need to use the new and improved Z-score formula, which takes x bar, the sample mean of 43, subtracts the population mean mu, 46.2, and divides that difference by the quotient of 8 divided by the square root of 50. And we get negative 2.83 when we round to the nearest hundredth. So the probability that x bar is less than 43 when standardized is equal to the probability that z is less than negative 2.83. And while the picture should still look the same, the area under the curve is much, much smaller. So the probability for a single occurrence you could see is much greater than the probability of the average of 50 occurrences being in the extremes. Thanks for tuning in, and again,